I've never been in a room with so many philosophers before, and actually, it's not bad. In fact, this actually one of the best meetings I've been to. So, E.O. Wilson, one of the great biologists of recent time, in one of his final works, urged that we think about a science of consilience. And by that, he meant the unity of knowledge. He lamented the fragmentation of knowledge and the resulting chaos in philosophy, which he said were due to the artifacts of scholarship. And in his writings, he seemed to suggest a fundamental role for mathematics. He said mathematics, because of its effectiveness in the natural sciences, seems to point arrow-like toward the goal of objective truth. Indeed, even referring to Wigner's famous essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. But he seemed unconvinced because he wrote that logical positivism, the notion that the philosophical problems worth studying are just those that are subject to logical analysis, is more commonly studied in philosophy like dinosaur fossils are studied in paleontology laboratories to understand the causes of extinction. But I'm going to argue that math is, in fact, the unifying discipline for consilience because it helps us to grapple with a bunch of things we want to know about. And with complex adaptive systems and emergence, which is going to be the center of what I'm going to talk about today, and to relate the reductionistic and holistic perspectives in understanding a whole bunch of things: scaling, emergence, pattern formation, critical transitions, and where I'm going to end up today, conflicts between interests of individuals and the collective good. The unifying theme underlying complex systems research involves relationships across scales. How do we see the forest instead of just the trees? How do we see the flock instead of just the birds? These are starlings, except for the one hawk that's driving things, which you may be able to pick out. And how do we understand the transformation of materials in terms of the molecules that make them up? In complex systems theory, one of the great and most influential papers was written by Phil Anderson a little more than 50 years ago. It's called More is Different. It was written to his colleagues, but it applies across the disciplines. This was in 1972, in which he said the ability to reduce everything to simple fundamental laws doesn't imply the ability to start from those laws and reconstruct the universe. And in fact, a less known paper, but one I think is a beautiful read by Francois Jacob, another Nobel laureate in 1977, called Evolution and Tinkering, argued that evolution is a great device, evolutionary models for understanding how we came to be where we are, but not so good at prediction. He said you must analyze complex systems at all levels. And the second point he made concerns predictions. He said, is it possible to make predictions at one level on the basis of what's known as a simpler one? And he said only to a very limited extent. The properties of a system can be explained by the properties of its components, but they can't be deduced from them. Starting from the fundamental laws of physics, there's no way of reconstructing the universe. There's too much unpredictability in terms of the emergence of macroscopic features. Ecosystems and the biosphere, which is where I spend most of my time working, are complex adaptive systems. That means they're heterogeneous systems, collections of individual agents that interact locally and evolve, and I don't necessarily mean in a genetic sense, based on the outcomes of those interactions. But not only the ecological systems, but also, excuse me, the socioeconomic systems with which they're interlinked. The fundamental macroscopic properties of the biosphere emerge from lower level interactions, things like species abundance, distributions that you heard Chris Kemp's talk about as his starting point, energy flow, nutrient cycling, ecosystem services. These are the macroscopic features that we are to a large extent interested in dealing with issues like sustainability. They emerge from the more microscopic interactions, but we don't fully understand that relationship. In the same way as emergence typifies problems in economics, the link between microeconomics and macroeconomics, we face the same problems in dealing with ecological systems. So this all implies a need to relate phenomena across scales, from cells to organisms, to collectives, to ecosystems, and up to the biosphere, and the linkage with uh, the social and economic dimensions, and to ask questions like, How robust are the properties of ecosystems? Are we endangering them? And how does that robustness of the macroscopic properties relate to ecological and evolutionary dynamics on finer scales? Are ecosystems at critical points facing sudden transitions into new and perhaps less um, positive situations? And one of the most difficult questions is, how do we manage the commons across scales and conflicts of interest, from individuals to nations to the biosphere? From a mathematical viewpoint, I can collapse these into understanding emergence and pattern formation, robustness and critical transitions, and cooperation and collective intelligence. And I'll touch on each one of those in the time I have left. So sustainability has to focus on the macroscopic features in the same way that we approach similar problems in physics, while recognizing that control of those rests at lower levels of organization. We all recognize that when we boil water to make tea, this is the result of lots of molecules moving around and interacting with each other. But most of us don't think of that every time we boil water. We deal with the macroscopic features. Uh, Bird flocks and fish schools have been of great interest to me, but to other ecologists. This from from my former postdoc and colleague and cousin. We've set out, me, meaning I and a lot of collaborators, in trying to develop these uh, comparable statistical mechanics for dealing with these systems. And listening to the talks earlier today, I will argue that these problems are harder than the comparable problems in physics, for all the reasons you heard before, but also because of the high degrees of nonlinearity and the interference that goes on. So with Glenn Flarrell, Danny Grunbaum, who was a former student of mine, and Don Olson, I wrote a paper 25 years ago, which attempts to develop this nonlinear statistical mechanics, essentially, in this taken from Danny's thesis, beginning from Lagrangian rules where individual fish or individual organisms are given uh, a set of rules, essentially force equals mass times acceleration. But the forces include not only the forces from the physics, but their tendency to align with or move towards or away from other individuals, to develop statistical mechanics of the whole population, and then to proceed from there by an appropriate limiting process to an Eulerian description, um, which well represents what's going on. It's nowhere near as easy as doing the same thing for molecules that are banging into each other and not making decisions. Similar sorts of models, scaling from individual based models like these trees growing and shading each other out and, and spreading their propagules around, can be used to develop models of the dynamics of forest ecosystems, and then scaled up to the globe as well with their interaction with the physics. And this from McFarlane's group at MIT. Similar models can be developed for ocean systems and other ecological systems. Pattern formation has been one of the central themes of mathematical biology. This is a rarely observed animal here, but the striping patterns and the spot patterns on animal coat patterns, the simplest sort of examples that come from developmental biology, can be well modeled using models suggested by Alan Turing, who was interested in more general problems of development. And if you're interested in this, I recommend Jim Murray's book uh, from about 30 years ago. So that deals with the problems of emergence and pattern formation. What about the robustness of these and the potential for critical transitions? Well, we know that stock markets crash and recover, that critical transitions occur in physiological states, like migraine headaches or seizures or atrial fibrillation. And when you go to the doctor, even if you're healthy, at least when you're my age, you will at least go through regular EKGs to look for signals that are early warning signals of sudden transitions. Those sorts of transitions are widespread. This is Martin Skeffer's book looking at critical transitions in nature and society. Martin's been very interested in early warning indicators of critical transitions. So can we read the tea leaves? Are there early warning signals? Well, borrowing a lot from physics, a lot of transitions have characteristic signals, and these have gotten a lot of attention. Thinking about the ball on the landscape that you see here and the rate at which it might return to equilibrium, as the system begins to lose stability, often it's the case that it's because this this bowl that it's sitting in gets flatter and flatter until it ultimately might disappear. And you see what's called critical slowing down, increasing variance, increasing autocorrelation, and maybe flickering among states. Physicists will recognize that this is characteristic of second order phase transitions. But this fact tends to be ignored. This is a very promising area, I think, in looking for early warning indicators. But um, it's want us to be there's a lot to be done because there are lots of other sorts of transitions that don't show these signals. It reminds me a bit about one of the first papers I read in mathematical biology when I was starting out in the field more than 50 years ago from Rennie Tom, who characterized the sorts of transitions that could take place in a restricted set of systems, gradient systems in particular, and characterized what he called the elementary catastrophes. And that was very powerful bifurcation theory, but it became oversold. A implied B, and people saw B and they started to say, well, that must be because A has caused it. Doesn't work that way. And so the whole field of catastrophe theory sort of collapsed on its own. The importance of critical transitions like these in the ecological system raises management challenges and takes me to the last part of what I want to talk about and what occupies most of my time now, which is dealing with cooperation and collective intelligence. From microbial systems to socioeconomic systems, for beginning from things like bacterial biofilms that keeps dentists in business, and the cellular slime molds that you see here, which are paradigmatic examples of pattern formation, um, all up to ungulate herds like these wildebeest herds in the Serengeti. These are self-organized patterns. The bird flocks that saw before, the fish schools. This is this is one wonderful snapshot of the starling flocks forming sort of a super starling um, in order to help deal with the predation. Whether this is intentional or not, I don't want to conjecture, but these macroscopic patterns do form. So this inescapably leads to conflicts between levels. Um, all too familiar example to us are the tumor cells, which grow at rates which favor them in the short term relative to other cells in our bodies, but ultimately may lead to the demise of the body. Want us to wonder whether we are the tumor cells for the planet, favoring short term uh, growth without concern for the long term consequences. So, dealing with these conflicts and how they're resolved through evolutionary processes in ecological system gives us a lot of insight perhaps into how we might deal with similar planets problems for the planet. And the need to scale from individuals to ensembles and backs, like these bird flocks, fantastic. It took, so too with human societies. So in those bird flocks, which have been well studied for a long period of time, it's been observed that birds pay attention to about their 7 nearest neighbors. So why? Um, my colleague Naomi Leonard and her group showed that this maximizes the robustness of the group. But the question that we then posed was, well, so what if it maximized the robustness of the group? Why should the individual birds care about that? And so our student, Eleanor Brush, approached this from a game theoretic point of view. One can begin by doing what Naomi and her group did, which they asked, what's the group optimum? What sorts of behavior would be best in the interest of the group? That's the same way we approach problems in dealing with sustainability and the overuse of resources. But will that survive? Is that a game theoretic equilibrium? Game theory is not dead. Uh, Game theoretic solutions can be applied to ask if individual birds are maximizing their own fitnesses, what answers do you get out? And Eleanor, in her thesis work, approached this question, and we published together. Um, and she showed that it depended on the task being carried out. Seven might work in those situations where the birds were trying to confound predators, but it didn't work if the birds were aggregating for the purposes of finding resources better. So a game theoretic approach was essential to understanding what was really going on in nature. And a game theoretic approach, and I'll come back to this at the end, is really central for understanding how we relate to others in dealings with with the problems of the planet. So can cooperation be extended to the global level? Public goods problems like the tumor cells, but also like the more familiar, perhaps pictures of fishermen exploiting a common resource and competing with oil rigs and other uses, are widespread in socioeconomic and ecological contexts. How do we achieve cooperation in the collective good? How does nature achieve it? Whether it was those bird flocks you saw before, aggregating together, or fish schools, uh, which combine to deal with a larger predator. This was first raised by William Forster Lloyd about 2 centuries ago, where he talked about the commons, and picked up in the middle of the last century by Garrett Hardin, who talked about the tragedy of the commons, which I suspect everybody's heard about. And for him, the solution to dealing with the tragedy of the commons was mutual coercion, mutually agreed upon. But by that, he meant that people would band together and develop governance structures or police forces that would enforce cooperation from the top down. But Eleanor Ostrom, Nobel laureate of about 10 years ago in economics, showed that this was not necessary, that at least in the small fisher societies that she worked in, it, cooperation came from the bottom up, came through the development of social norms and procedures, and didn't require top down influences. And then she turned her attention at the end to building the bridge between these local solutions and global solutions, arguing for what she called polycentricity, local agreements that could then um, be built together to develop a global agreement. So, how do such social norms become established? What's the role of leadership? How is consensus achieved in democratic societies under incomplete information? What's the role of the unopinionated, um, the middle group? And in separate work with Sam Wong, I've been looking at alternative voting systems to try to get more democratic governance. And one of the tendencies that we've seen is not only that have the Democrats and Republicans increase the distance between them along axes of opinions, but the number of people who identify themselves as independents has increased greatly and is larger than the number who are associated formally with either party. So we need collective intelligence. Collective intelligence is a public good. This is a paper that Naomi and I published 2 years ago. But as we know, unfortunately, political polarization is on the increase and it threatens democratic governance. And we actually organized the special issue of PNAS a few years ago um, to deal with models of the dynamics of political polarization. Social norms are key, and they can change rapidly. Um, Attitudes, the most familiar example is perhaps most dramatic example is foot binding in China, which was quite stable over long periods of time and then disappeared relatively quickly. Attitudes towards smoking in public places, racial equality, gender equality, could show you data on climate change. And we saw what happened during the pandemic as attitudes towards uh, key aspects of public health changed and unfortunately continue to change. So game theory is not dead. It's central to understanding cooperation, collective intelligence, and the dynamics of these social norms. So I'm running out of time. Um, and at all levels, mathematical thinking, I'm arguing, can address the fundamental problems of complex adaptive systems, from the scaling laws up to the dealing with the conflicts between the interests of individuals and the interests of collectives. The mathematical approach unifies disciplines and allows the easy transfer of successes in one discipline to another. This was, I think, Wilson's really definition of what consilience ought to be. My colleague Bob Austin, who's probably known to a lot of the physicists here, uh, put me on to a slide from Dean Astumian, whom I don't know, but others might know, who had a research grant rejected. And he said, and the review said, the work described is focused on important systems, very interesting. It seems, however, the author proposes to do mostly thinking. And it's not clear that the NIH should support thinking. Well, I'm going to argue that we need more thinking and that mathematics helps us to do that. Galileo said that the universe is written in the language of mathematics. And I argue that we have reason to continue to anticipate and to enjoy what Wigner called the unreasonable effectiveness of mathematics in the natural sciences. And with that, I want to thank the various agencies and Princeton University that funded my work, and especially, Bill Miller, who's already been thanked, who's been so important both to our work and to all of the work in natural philosophy. Thank you.
I feel a little bit inadequate talking in this crowd. I loved Janan's talk. Many of the points that I was going to make came up there. Life is self-referential, or if you prefer, self-interfering. The nature of reproduction is that the survival of organisms in the complex ecology that was just talked about determine which genes get to be reproduced and what sort of organisms you see. So in this recursive process of life, the distinction between what is cause and what is effect gets complicated. Now, I want to talk a bit about meaning and purpose in the world. All meaning is metaphor, the representation of things by other things that are not the same. If you think about consciousness, whatever it is a metaphor of the world. Qualia, let's take the qualia of color. Whatever they are, they're clearly not the things that they are representing in the world. They're representing one thing by something else. Now, mathematical models are disciplined metaphors. We use X to represent something in the world, say slugs, and Y to represent something else in the world, say lettuces. Then we analyze the relation of X and Y using mathematics. We imagine that slugs and lettuces behave like X and Y in the model, and then use how X and Y behave in the model to understand how slugs and lettuces behave in the world. So these models are useful in general, though each slug and each lettuce plant is an individual. Mathematical models soon run into difficulties when dealing with interactions among small numbers of things. The three-body problem in physics and the two-locus model in genetics are analytically intractable, except in special cases because of the combinatorial explosion of interaction terms. A path out of this impasse has employed statistics and the laws of large numbers. Each particle is represented by a mean and deviation. The deviations cancel, and we are left with mean behavior. The cancelling of deviations occurs with high confidence when we consider the behavior of an ideal gas, but is less reliable when the particles are living things. Biological individuals are not readily interchangeable. Each possesses personal idiosyncrasies. There can be intervention from above or interference, as well as emergence from below. The idiosyncratic choices of living things can cause critical transitions that were talked about in the last talk that cannot be explained mathematically except by metaphor. The outcome of the 2000 presidential election was determined by hanging chads, Karl Rove's decisive action to shut down the recount, the concurring opinions of 5 out of 9 justices of the Supreme Court, and Al Gore's decision to concede. If Al Gore had been Donald Trump, the world would be different. But as Hannah Arendt said, in the world of choices, it's impossible to know the consequences of the choices that we do make with any certainty. We can attempt to predict, but we don't know, partly because many other people are operating interference. The reason choices of living things can intervene at the microscale to have large effects at the macro scale. Choices are creative for good or for ill. And by talking about our choices, I'm also identifying with all living things, including slugs and lettuces. I want to take the role of an Ismailian demon. Could the members of the audience raise their right hands? Thank you for positive interference. You can put them down. What just happened? My intention to make a rhetorical point caused ions to move across membranes, protons to go across mitochondrial membranes, actin to slide past myosin, all sorts of things happening. So my intention to make a rhetorical point interfered at a molecular level to cause things to happen that wouldn't have otherwise happened. You raised your hand by my fiat, my let it be done, by a pronouncement from on high. I intervened, perhaps interfered, in your body at the molecular scale, but I did not have complete control. I counted on your willing cooperation and knew that some of you would be unwilling to play along with the game. You have freedom of choice. I believe Charles Darwin is the great unappreciated physicist of the 19th century because he unified the world of causes with the world of reasons. Natural selection is a purposeless physical process without goal or direction that generates goal-directed agents who act for good reasons and use observations of the world to inform their choices. The meaningful information in our genome has come from the environment that selects, including the complex ecological and social interactions of individuals of many species. The ecological macrocosm determines the molecular microcosm. Meaning came into the world once random changes to a genetic text were repeated because the unseeing environment saw that they were good. From the beginning was the recorded word. Darwin is not considered a physicist because his work is free of formal mathematics, although richly quantitative. The origin of species does not contain a single equation, but evolutionary theory is now replete with mathematical models. Nobody can argue with mathematical models. That is one of the values of mathematics. But when it comes to modeling the living world, there can be endless arguments about what you put into a model, what you leave out, and endless arguments about what the model means, because metaphors can be interpreted in many ways. Sometimes mathematics misses the point. The theory of evolution by natural selection is my candidate for consilience between the sciences and the humanities. Natural selection is more a poet than an engineer. Organisms mean many things at once.